Hey, so welcome to the first chapter of the of our class of behavioral statistics. This is chapter one, Introduction to Statistics from the Gravetter textbook. And so really it's going to be sort of a table setting chapter in terms of like presenting you with some terms and ideas about how to kind of think about statistics going forward. We won't actually be computing any statistics in this first chapter, so maybe there's a bit of relief there. I just heads up, I was trying to do full screen and do my video share at the same time, but it was saying that I couldn't share my screen when it was in full screen. So for now, I'm just going to have the slides presented this way. And I think you have access to those slides as well, so you can follow along however you'd like. Um, and depending on, the length of future chapters, these videos might be broken up into one or two, or three, I guess. I don't know. Depends on how long the chapters are. I feel like chapter one, I can probably go one video and that should be fine. But I do recommend probably take breaks. Maybe you don't take this all in at one time. Maybe you break it up into parts or, halves or however you want, but that's up to you. Take a restroom break if you need to, pause, reflect, whatever. Um, so what I would recommend always is when we start these chapters, you're going to have learning outcomes at the beginning of each chapter. And my recommendation is to use these to guide your learning as you proceed through the chapter, and also use this to test and make sure you understand the chapter we just covered. So the outcomes for this chapter, no key statistical terms. So my recommendation, anything that's underlined or if it has a slide dedicated to it, that's a statistical term or a measurement term or a research term, and it's probably important. So make sure you know what that is, know the place of statistics in science, and then also understand summation notation, excuse me. So as far as stats, I mean, statistics does involve math. We really can't get around that. It does require basic math skills, addition, subtraction, multiplication, division, really the PEMDAS stuff, the please excuse my dear Aunt Sally, the order of operations, plus we throw summation in there. Those are the kinds of skills we're talking about. So basic, hopefully nothing you haven't encountered before. However, I do want to be really upfront with you that if you don't really feel prepared, or if your math skills are inadequate or are lacking, that will make this class more difficult for you. I'm not saying it makes it impossible, it just makes it more difficult. And so you can evaluate some of those skills yourself. If you have the Gravetter textbook, you can go to the Appendix A in the back. There's a math skills assessment and review and assessment to kind of figure out where you maybe where you stand as far as those math skills needed to be successful in the course. And that's really, it's not to make you feel bad about your math skills or anything like that. It's meant to just show you realistically, hey, these are the skills necessary to be successful in a statistics class. Okay. So when we talk about statistics, what we're referring to are a set of procedures or statistical procedures. And you could think of those kind of like, having a toolbox, and each statistical procedure is kind of like the tools we might pull out and use for different jobs. Handyman jobs you might do around the house, just as the metaphor. So ultimately, we use statistics to organize and summarize information, in this case, data, which we'll talk about in a future slide. And we also want to know and be able to determine what are the conclusions we can take away from all that information that information we've just obtained. The goal of the procedures of statistical procedures are to provide an accurate and meaningful interpretation of the data that we have, and then also provide a way to standardize the process for evaluating our data and going through those procedures, kind of making sure that, when somebody says they're running a correlation study, everybody knows what they're talking about because that's been sort of standardized, so to speak. Okay, so some key terms that are really important for understanding in statistics are the difference between population and samples. A population is everybody who belongs to a particular group. They're everybody who, if we're interested in a particular group to study, the population is everybody who belongs to that group. And they tend to vary in sizes, of course, but often when we're talking about a population, we're talking about a group that's going to usually be pretty large. So, it could be all students at OCCC, for example, would be considered a population. Now, the sample is a set of individuals that we select from that population. I say we, I say, potential researcher in this case, that you will select from the population, hopefully intended to represent the population in your research study. And hopefully that sample is representative of the actual population, meaning it's similar in characteristic, for example. But there is a relationship between these two concepts. They are related. They're separate concepts, but they're related. So population, it's everybody who belongs to that group. We select a sample to study that population. We select a sample of participants from the population. The sample of the study, they're selected, and the results from the sample are used to generalize about the population. We take the information we learn about the sample to better understand the overall population. The reason why we don't just evaluate everybody in the entire population is it's timely, it's costly, maybe not everybody will participate. I mean, think about, if you were making decisions at OCCC based on the attitudes of the student population, it would take a long time to get every single student's, attitude about any given topic. And it might, maybe not everybody replies to the survey you send out. I mean, in fact, most probably won't. So usually we're talking about a much smaller sub. The sample is a subpopulation, or it's a much smaller group taken from the population. Some other key terms to be aware of: variables and data. Variable is anything that changes, and the fact that it does change is the why we want to measure it and we want to capture it and understand it. If something didn't change, it really probably wouldn't be in of our much interest to research it. So really, we're talking about anything that can take on multiple conditions or characteristics, and we try to capture that variation through data, which is the plural of datum. Data is our measurements or observations of that variable. A data set is all of the collection. So let's say, for example, we wanted to know about people's attitudes about parking at OCCC. If you send out the survey and let's say 100 people take it, well, on your whole data set of all of those 100 people, you have one line, let's say it's student A, that's their responses to that measurement. And then the collection of all the rest of the 100 students who filled out that survey is the data set. It's the entire collection of observations in this case. A datum is just one singular score. So maybe it's your reply to one single answer. Do you like the parking situation at OCCC? Yes or no. And if you say yes, you get a zero. If you say no, it's a one. That's how it's scored. Kind of, I don't know. Just giving you an example. So data set, datum, very similar concepts and ideas, but all kind of, different as well. Also need to be aware of this idea of parameter versus statistics. Parameters are used to measure and describe populations, and statistics are used to collect data and measure and describe samples. So, for example, you might see a parameter. One you might have seen is a census. When we give out the census every 10 years in the country to kind of see how many people are in this country and what their kind of background is, and who, what the structure of a household is, things like that. We're showing those population. Once that's presented, it's population parameter. It's the census. Statistics might be the individual surveys we use to collect data from individuals. However, we're deriving that information, from the sample to the population usually. Some other important terminology: descriptive versus inferential statistics. Descriptive statistics are just like they sound. They're intended to describe the data, to organize it and simplify it. I mean, because think about it, if you data really is just like a data set. If you collected, I don't know, an attitude survey, people's attitudes about a politician, for example, usually what that's going to come back to you is a big data set full of just numbers. Maybe it's Likert scale numbers that show up on the in your data score in your set. And you have to find a way to make those numbers make sense to people. It wouldn't really make sense to write a paper or go to a conference or give a presentation and just show a bunch of numbers, like just a collection of your data set of numbers. Nobody will understand what that means. So we use statistics like descriptive statistics to simplify, to take all those numbers and maybe turn it into a few key numbers that really stand out. Some examples of this might be presenting your data in forms of tables, graphs, or just presenting the averages to really give people the quick kind of summation of your data instead of obviously just boring them to death by showing them all of your data. Inferential statistics are what allow us to make those generalizations from our sample to our population. Um, these are what us allow us to interpret actual experimental data. Descriptive statistics aren't necessarily data we might collect those for our research, but when we talk about inferential statistics, we're talking about really getting into like experimental design. Are we making a significant difference or not? And that terminology will come up again more and more. Some other terminology you're probably going to hear in this course, and just when you hear about statistics in general. Oh, I just mentioned it. Yeah, statistically significant means there is actual meaningful change there. There is a real difference there. Let's say when we're comparing two groups. That's what it means by statistically significant, and we will touch on that in more future chapters. Sampling error or margin of error, that just refers to that kind of the difference between our sample and our population. And I think we're even going to cover that on the next slide. Yeah, exactly. So when we talk about a sample, our sample can be really close to our population, but in theory and in practice, it's never identical to the population. There's going to be some inherent error built in, but that doesn't necessarily mean there's something wrong or it's not a value judgment about error. Really, it just means simply there's a discrepancy that exists between our sample statistic and our population parameter. The more representative our sample is, the more our sample looks like the population, the less likely there is to be error. But the fact that we're not truly, collecting data from every single person, we do kind of build in some theoretical error there. And a lot of times you see this represented in things like political polls. You'll see candidate X is favored to win, 48 to 43 with a sample with a plus or minus, 4 percentage points. What that means is the candidate, like let's say the candidate in favor, if they're saying, okay, they're 46 points plus or minus four, really what they're saying is their outcome could swing as wide as 42 on the short side of things or up to 50% is on the high side of things. It's kind of like that margin is kind of the error we're building in on either side. And then the actual predictive score is kind of that hinge point, so to speak. So the greater the degree of the margin of error, usually what we're saying is there's a larger degree of variation between our sample and our population. Okay, so this is kind of the role of statistics and research here. Let me kind of zoom this in for you. Sorry. This is comparing two different studying methods, our population or college students in this case. We're going to collect data from reading scores. We have sample A, they read from a computer screen. Sample B reads from printed pages. So that's kind of the variation there. That's what we're changing. That is our independent variable in this case, is the method of reading the scores. We then collect the data. We're going to describe the data in terms of descriptive statistics. What is the average? What's the average score? It's an 11 for sample A. It's a 15 for sample B. Sorry, here, let me adjust my cord a little bit here. Our inferential statistics, we can look at the sample data, show a 4 point average difference. That's our descriptive. Now we want to know inferentially, is that enough? Is that a significant difference? Is that a real meaningful difference? There actually is no difference between the methods. Between the sampling is due to chance in this case. There is a real difference. That's the kind of information we're trying to find out. We're trying to make the inferences. Is there nothing going on there, or is there actually something going on there? And we will come back to that and spend more time in future chapters on that specific topic. So I just kind of wanted to show you all those previous slides kind of in action. Okay, here's where we're going to do a couple quick comprehension check questions. This is where you can stop listening to me talk for a minute and just make sure you understand. I recommend you answer these questions at home, maybe pause the video, write your answers down, or just keep them in your head. But it's multiple choice A, B, C, or D. Here we go. A researcher is interested in the effects of amount of sleep on high school students' exam scores. A group of 75 high school boys agree to participate in the study. The boys are A, a statistic, B, a variable, C, a parameter, or D, a sample. So you could pause the video here, write your answer down, make sure you understand, then come back. I'll give you a moment. Okay, let's check the answer. They are a sample. 75 high school boys agreed to participate in the study, assuming at this high school there are more than 75 boys there. There could be 150 boys and half of them agree to participate. Who knows? I'm just making up a number. The next one, there's actually two questions. You're going to answer true or false to both of them. First one, true or false? Most research study data from samples. And the second one, when sample differs from the population, there is a systematic difference between groups. All right, so you need to answer true or false for both of those. So again, pause, we'll come back and reveal the answer. Okay, here we go. First one is in fact true. Samples are used because it is not feasible or always possible to measure all individuals in a population. And number two is false. Sampling error due to random influence may produce unsystematic group differences. That's not really anything. There's no any kind of bias or anything going on there. Sampling error is kind of a natural part of the sampling process. We might try to minimize it as much as possible, but it's sort of bound to happen on some levels. Okay, so some back to sort of ways of thinking about statistics and science. We're talking about this sort of empirical, when we say where do statistics fall in terms of science? Well, science is an empirical undertaking, meaning we are trying to derive truth and understanding about the world around us by making observations of what we see around us. So a lot of times we're talking about collecting data through observations, just seeing what's happening and maybe writing it down, measuring it, giving out surveys, collecting it in terms of trying to see what varies. We're collecting scores in terms of data by observing and measuring variables of interest. And this is where we talk about applying those different procedures that we're going to go through chapter by chapter in subsequent chapters as a way to better understand and make sense of our variables that we're interested in. Okay, some more table setting terms, constructs and operational definitions. Constructs, these are the attributes or characteristics that cannot be observed directly. These are used for describing and explaining behavior. And then operational definitions, these are ways that we decide to operationally define a particular variable. For example, when we want to measure that variable for research, and we use that in terms of making measurement and a definition, for this kind of hypothetical construct. So, for example, there is this construct of anxiety, this state of maybe internal dread or panicked or worrying, but that is very much an internal experience. So we have constructs as a way for people to describe that internal experience. So if we were interested in studying anxiety, well, we have this construct of anxiety that we want to address and answer, but we need an operational definition in order to be able to study and capture it. And there are a lot of different ways you could, for example, you could have people self-report their levels of anxiety. You could hook people up to some kind of device that might collect their heart rate before and after an event. You could do the same thing with their galvanic skin response. There's all these different ways we could operationally define what we mean by anxiety. And as the researcher, you have to be pretty crystal clear about what the construct you're interested in researching and how you are then defining the way you go about measuring it. So, and that's, when you're writing like a research paper, that's what the literature review essentially is you outlining your constructs of interest and then talking about how you're going to measure it or operationally defining how you'll measure it. Okay, so when we talk about variables, the things that we're interested in measuring and capturing, we can look at them in kind of two broad categories. We have discrete versus continuous variables. Discrete variables, they have separate indivisible categories that, you belong to. There really isn't any kind of value in between that category. So, for example, it could be like your class standing, being a freshman at OCCC versus being a sophomore at OCCC. Those are very discrete categories, and there's no kind of in between. You're either a freshman or you're a sophomore. Versus continuous, there really is infinite number of possible values in between, in between any two observed values, and think about this as more like, your height. You could be 70 inches, and there could be people who are 75 inches, and there's people all in between. There's an infinite number of possible values kind of in a scale like that when we're talking about measurement. So discrete variables might be not always, but might be somewhat more qualitative in nature, not necessarily always the case. First, because continuous variables tend to be more quantitative. But again, those are not always the case. It's just kind of a maybe an easier way of thinking about it. Okay, so here's an example of a continuous variable, like if you were measuring a quantity, or I guess this is weight in this case. you know, your weight might be 150, or you might tell people it's 150, but that maybe it fluctuates somewhere between 159 or 149.5 and 150.5, somewhere between there. We would call those 2 points the real limits. Once we pass the threshold in either way, maybe we don't describe ourselves as 150 anymore. That's kind of another important term to think about. The boundaries of those intervals on continuous data, on a continuous number line, these are the boundaries that separate. What is the boundaries of saying how long do you continue to say you're 150? Maybe once you start getting really past the 150.5, then you might start talking about, oh, I'm over 150, I'm 151, I'm 152. I mean, that's kind of a silly example there, a little bit if you're thinking about your weight, but that's just more kind of table setting and examples to hopefully make that makes a little sense. We also have different scales of measurement, where we assign different thing measurements and measurements will assign individuals or events to the categories. Categories can have names. They can be qualitative in nature, having names, being introverted or extroverted, unemployed, employed, for example. They can also be in numerical values, your height, 68 inches, or your weight, 175. But the categories used to measure a variable make up what we call a scale of measurement. And that's what we're going to take a look on the next slide. We have nominal, ordinal, interval, and ratio scales of measurement. Nominal tends to be, I mean, nominal kind of, it's more like name. It's a measurement in terms of name. It's a label or a category. There's really no quantitative distinctions whatsoever. Some examples might be one's gender, a diagnosis. Either you have maybe the disease or not. Let's say you test positive for COVID or you don't, for example. Experimental or control if you're in a research study. Ordinal, we do have categories, and they're organized by like size or magnitude. For example, there is some kind of distinction between the different classes. So maybe it's your rank in your class. Maybe that's based on your GPA, your size of clothing, Olympic medals. Gold for first place, silver for second. Interval scales of data. They have their ordered categories, their interval between the categories, and it's of equal size. There is an arbitrary or absent 0 point in this case. Some cases might be temperature, IQ, or golf scores. Temperature, the lower it is, the colder it is, the higher it is, the more warm it is outside. IQ, we relate that to problem solving. So the higher you score on an IQ test, the more greater ability we perceive you to have in terms of problem solving cognitively. And then finally, ratio. We're talking about still has ordered categories. There's an equal interval point, and there's an absolute 0 point. Number of correct answers on a test, time it takes to complete the task, gains in height and weight since last year. If you're somebody who kind of tracks those things, so we can actually compare. A lot of this is like for comparative purposes. So like the number of correct answers, you can see, oh, well, I got 25 out of 30 this time, and the second time I took it, I got 29 out of 30. I can actually see an improved ratio in my score after studying or after intervention. Okay, here's another quick learning check. So again, I recommend pausing the video to make sure you understand before moving forward. A study assesses the optimal size number of other members for study groups. The variable size of the group is A, is it discrete in interval, B, continuous and ordinal, C, discrete and ratio, or D, continuous and interval. Pause the video and maybe check your comprehension before moving on. Okay, here we go. It's discrete and ratio, the number of members for study groups. We have a discrete category and ratio in this case. Okay, same thing as before. True or false, decide if each statement is either true or false. First one, variables that cannot be measured directly cannot be studied scientifically. True or false? Research measurements are made using specific procedures that define constructs. So pause here, maybe write your answers down, and let's see, come back in just a moment. Here we go. First one is false. Constructs or interval states can, internal states can be observed indirectly, but can be operationally measured. And then true, operational definitions assure consistent measurement and provide construct definitions. Awesome. Hopefully you're doing well on these as we go along. Now we're going to take a look at some different types of data structures, different research methods, and statistics used at different points of the research process. So data structures are first is descriptive research, really just focusing on individual variables. Maybe we're just interested in anxiety, maybe we're interested in imposter syndrome, maybe we're interested in, I don't know, some kind of construct or idea. Usually it's one variable we measure per individual. We use those statistics to describe the observed variable. Maybe it's categorical or numerical, but we're not really interested in the relationship at all between the variables. Maybe this is a new topic that we're interested in and kind of adding to the literature on, but we're really not trying to manipulate or really see anything as far as relationships go. This is usually just kind of a good starting point for research. However, maybe we get curious and we start to see some connection between our research, our variable of interest, and other variables. So we might look at the relationship between those variables. So at that point, we need at least two or more variables we can observe and measure and collect data on, and then we can use statistics that we can look at the data from the two or more variables, and try to determine, hey, is there some kind of relationship happening here? Every time this variable happens, and does it change variable Y? We can really start to dig deeper into that, at least statistically. And that's when it gets into like the correlational method. This is usually the starting point as far as relationship between two variables. We're trying to see if there is a relationship between two variables. We have one group of participants, we measure them for two different variables, and the goal is simply to describe the relationship, the type of relationship, and also the magnitude. Is it a negative or positive? And how strong is that relationship? We're really just looking at patterns in the data to reveal the existence of a relationship. However, we can't really say if there is a relationship. We don't really know much more than that because we're not manipulating, we're not experimenting with any of the other variables of that could be at play. So here's an example. Sorry, this is an example. It looks like collecting data on time spent on Facebook and academic performance. And so we can kind of see we have one, two, three, four, five, six, seven, eight participants, and we rank them based on their academic or their Facebook time. And also we can clearly see if you take your line down this correlation, this table, we can see what would be a negative correlation. As Facebook time goes up, we can see that academic performance goes down. There could be other factors at play because we're only collecting data on these two variables. There might be other things going on. We can't necessarily say that Facebook time causes academic performance to go down. We just know they are related. Okay, correlation's really cool, but I just kind of outlined it. Really, all it does is demonstrate the existence of the relationship. It doesn't really provide an explanation, like a causal explanation. It doesn't really say, "Hey, this variable causes the other variable." It just says they're related. It's a starting point. We have to perform other statistics, which we'll talk about later on, if we really want to dig into the nature of the relationship. So this is when we start to get into data structures involving experimental and non-experimental, where we can compare two or more groups based on some kind of outcome score we're interested in. We usually have one variable that defines the groups. Maybe you participate in an intervention and this group does not. This group takes the exam digitally. This group takes it on paper. Just some kind of variation that allows us to make the distinction between the groups. We're going to collect scores based on that are measured on a second variable. The experimental and non-experimental studies kind of use this structure, but there are some variations along the way we'll talk about. So here's one comparing two groups. We have experimental and non-experimental methods. We have one variable type of video game is used to define groups, violent versus non-violent. Some would play the violent video game, some would play the non-violent, and we can compare them against each other. Compare the two groups. I'm guessing this is non-experimental because maybe we're not determining who's in what group, or maybe we are. It would be experimental if we manipulated who is in what group. It'd be non-experimental if we didn't. Experimental method is the go-to in terms of research because it does allow us to make those cause and effect statements. We can not only see that there's a relationship between two variables, but we can dig deeper and say, here's why this is happening. We can give kind of a cause and effect statement. Because we can manipulate variables, we can manipulate the key variables, especially the independent variable, who belongs to what group, for example. Do you receive the treatment or do you not? Do you receive the placebo or do you receive the real drug, for example? Do you play the violent video game or do you play the non-violent video game? Usually what happens is you have an experimental group, the one who receives the treatment, and then you have a control group who doesn't receive the treatment necessarily, but is hopefully similar to your experimental group, but you can kind of use them as a way to like rule out kind of other outside variables, participant or environmental variables. Some other terminology, I've mentioned this before already, but the independent variable is what we manipulate. So if you're interested in like, hey, does this new antidepressant medication work or not? The independent variable would be who gets the antidepressant drug or does not. Maybe one group gets the drug, the other does not. Maybe one group gets 10 milligrams, one gets five, one gets none. The dependent variable is what we're collecting data on, what we're actually trying to measure. So in this case, if maybe we have a depression scale inventory that we give everybody before the medication trials, we give them after the medication trials, and we can compare the results. And so we have our dependent variable is collecting the data. The independent variable is what we're changing and manipulating. Just kind of an easier way to remember the difference between the two. So when we control things, we're trying to control. We can control in terms of experimental design. We can randomly assign subjects to their group, the experimental versus control group. We can try to match subjects in terms of making sure the groups are balanced. Like meaning, like you don't want one group to just be like way older or younger than the other group, or one group to be much more predominantly male or female, or maybe if you're talking about students at school, you don't want like one group to be all seniors and one group to all be, freshmen. You might want some balance amongst all the grades, finding a way to kind of match. You want to hold as much of those things as much as constant as you can. Our control condition, they do not receive the experimental treatment. They either receive some kind of maybe a neutral placebo treatment or just nothing at all. And this is what we use for baseline comparison. And then the experimental group obviously is the one who does receive the treatment, the experimental intervention that we're interested in. Okay, sometimes we have non-equivalent groups where researcher compares groups of scores, but they can't control who goes into the group. Maybe you're comparing two classrooms on a campus that you're allowed to research in, but you don't get to pick the classes because that's just who's available to you. So you have non-equivalent groups. Maybe they're similar in some cases, but not always in others. Might use a pre-test or post-test method of research gathering data at two different time points, maybe one before the intervention starts and again after the intervention is over. I come from an educational psychology background. That's a lot of what we do in ed psych is pre and post. We'll collect data from students before they begin an educational intervention just to see where they're at. And then we run the educational intervention, then we collect data afterwards to see if there are improvements. For example, let's say if you're doing like a reading intervention, you might want to, test reading scores before and after to see, hey, did it work or not? So here's an example again, two examples of non-experimental studies. You have variable one, participants, location. It's quasi-independent variable. It's not manipulated. People can't necessarily choose if where they're either at location X or location Y or some kind of variation. And then we have variable two, which is our verbal test scores. We're trying to compare, does maybe living in a suburban area or rural area, does it have any difference in terms of, your verbal test scores? But you can't manipulate and say, I know you live in the suburban environment, but we want you to go live in a rural environment and vice versa. You kind of just take participants where they are in this case. Another experimental is time. This is our quasi-independent variable. It's not manipulated, but it's used to create two types of scores before therapy and after therapy. And then we measure them on a depression scale, maybe before and after. Okay, here's another learning check. Researchers observed that students' exam scores were higher than more sleep than they had the night before. This study is A, descriptive, B, experimental comparison of groups, C, non-experimental comparison of groups, or group comparison, excuse me, or D, correlational. Go ahead and pause here, check your comprehension. Yeah, it's D, correlational. We're just looking at what's the relationship between sleep scores and exam scores. Next one, all research methods have an independent variable. And B, or next one, all research methods can show cause and effect relationship. Are these true and false? Go ahead and pause the video, make your answer. Both are false. Correlational methods do not have or do not need an independent variable. Nothing is being manipulated there. And then also only experiments control the variable of influence or environmental influence variables. They don't, we, those, other methods of research don't have that same kind of control. Okay, so notation, learning how to write and think about and put out your thinking in statistics, using operation and notations. You've learned again. Go to math, the appendix A to take a look at that. We're just talking about basic math skills, but there are some kind of summation or notation that's important to understand. A lot of times we look at scores referred to as X, usually a capital X. Sometimes it's a Y. Maybe if we're talking about more than one score set. N, a capital N is referring to the scores and the number of a population. So let's say if we were talking about the entire student population at OCCC, I'm just making up a number, but capital N would be 30,000, just as an example. Lowercase n would be the number of students we sampled from that population. So maybe if we're, in this case, it's only 500. So capital N for population, lowercase n for sample. Really, a lot of times what we're talking about, the statistical procedures we're going to use involve summing or adding up. The summation score is this Greek symbol here. It looks like an E, but really I believe it just stands for sigma. And it represents, or it's always followed by a symbol or equation that defines what is to be summed. So everything after it is what we're going to actually sum. Summation is done after operations in parentheses, squaring or multiplication, but it's done before addition or subtraction. So if you remember, maybe from math way back in the day, PEMDAS, please excuse my dear Aunt Sally, those order of operations, we're going to do parentheses first, exponent second, multiplication, division third, but then summation is in between that, then it's addition, subtraction. So here's a quick learning check to make sure you understand. So if we have this equation here. We have the sum of x squared plus 47 instructs you to what? Is it A, square each score? In this case, X is our scores, and then add to 47 to it, then sum those numbers. Square, is it B, square each score, add up the square scores, then add 47 to that sum score, add 47. So C, add 47 to each score, square the result, then sum those numbers. Or D, add up the scores, square that sum, and add 47 to it. Pause the video to make sure you understand and come back once you feel like, you have an answer. Here we go. It's B. We're going to square. Remember that, please excuse my dear Aunt Sally. Parentheses, we don't have that. Exponent, we do have that. So whatever each X comes up, we're going to square it. Then we're going to add it up to squared scores and then add 47 to that sum, excuse me. Decide if each of the following is true. The sum of x squared equals parentheses the sum of x squared. Are those the same thing? Also, the second one is sum of x times the sum of x is equal to the sum of x squared. Are these true or false? Just go ahead and pause the video here. Come back when you think you have an answer. Here we go. Oops, sorry. Top one is false. When the operations are performed in a different order, the results will be different, meaning if we perform these based on parentheses, this is going to give us a different answer than what comes out here. So they are not equal. This one is true. This is the definition of the sum of x squared. This is just kind of that foiling method. If you're familiar, if you remember foiling from math class as well. Okay, that's going to be it for chapter one. I know that was a lot. I feel like I just loaded a whole bunch at you. I'm sorry. Hopefully you broke that up into multiple pieces. Please let me know if you have any questions, concerns, thoughts, anything at all. Leave me a comment, shoot me an email, whatever works for you. But I'm going to stop sharing and I'll post this for you all to watch. All right, thanks. Take care. Bye.